Okay, good afternoon. My name is Jiechen Zhang, and I'm a PhD student at EPFL. And this is joint work with Jose Correa, my advisor Andres Christie, and Vasilis Livanos, and Victor Verdugo. So the question is very simple. On an online stopping problem, suppose we do not know the distributions, but only their moment. How informative are those moments for making online decisions? So let me start with the standard profit inequality model. There are random variables x1 up to xn, and arriving one at a time. When a value arrives, the decision maker must decide to either accept and or stop. Uh, Either accept and stop or reject it for forever, like this. So this captures the same tension that appears in online auctions or resource allocation hiring. The decisions are made sequentially, but they are irrevocable. So in classic models, the gamblers know the full distributions of each xi, observing their realizations online, and chooses when to stop, like this. And the profit sees the actual values are just, receives the optimum, which is the maximum overall the xis. And the celebrated result by Samuel Kane results saying a single threshold algorithm can achieve at least half of the expected optimum. And this is the baseline we should and this is the baseline we should keep in mind. So with full distribution information, the story is clean. One simple threshold is enough to get 1/2 fraction of the profit, and this is tight. So, but the full information assumption is still strong. In practice, we may not have access to the full information due to little data or noisy data or indirect access. And in those cases, the decision maker may see only partial information about each distribution. So the community has pivoted a lot to address these concerns. And as mapped out here, the literature generally tackles these through three paradigms: learning from the samples, or dealing with biased priors, or making decisions based purely on summary statistics like mean or variance. So the sample access model is very well developed. As you see, it is worth mentioning that the work by Rubinstein, Wang, Wenberg shows that one sample from each distribution is enough to recover 1/2. And another model gives the algorithm a prior distribution that is close to the truth, and this is related to distributionally robust optimization and algorithm with advice. So Duting and Keisenheim showed that 1/2 can still be recovered. And our work asks what happened when the summary statistics are moments, and this is natural because the data owners often publish like means, variance, or higher moments without revealing the raw samples or full distribution. Similar moment ambiguities are also common in distributionally robust optimization and mechanism design. But what is less well understood is that they're power in online optimal stopping. Okay, so here's the question. And for the model, so for each xi, the algorithm is given the expected value all the way up to the kth moment, but not the distribution itself. The benchmark is still expected value of the maximum of all the xi. And the goal is to understand the best possible comparator ratio as a function of n and probably in k. So, okay, one moment. We can start with k equals 1. So the algorithm only knows the means. And in this example, all 5 means are equal to 1. And if the very first realized value is 3, should we take it? So the answer depends on what the remaining distributions are. From means alone, the expected maximum of the remaining is at least 1 and at most 4. So in this case, we might want to take it. And you can probably see from here, some difficulty is that even the scale of the profit value is ambiguous. So some might have higher variance. And so the classic threshold proof tells us, like, if we knew the expected value of the opt, we could set a threshold that is half of it to obtain 1/2 guarantee. And more generally, as shown here, if we know the expected opt lies in the interval alpha and beta, then a threshold tuned to that interval loses only the ratio between alpha and beta. And so we can do this. Okay, we can set mu star to be the maximum of the expected value because the random variables are non-negative. We can't have this bound. And the left-hand side lower bound is because of the point-wise dominance of the maximum, and the upper bound is just because of union bound. So therefore, the possible profit value lies in the multiplicative range of n, which has only log n exponential scales. So here each scale is increasing at the size of 2. and the algorithm can choose, uh, one scale one scale uniformly at random and set the threshold that is assigned to that scale. So if we choose the right one, because the profits reward is contained in one of the bucket when in one of the scales. If we choose the right one, we can get 1 over 4 constant factor of approximation. And here the constant the constant can be improved, but it doesn't matter because it's still constant. And since this happens with probability about 1 over log n, then we can get a 1 over log n approximation. Okay, now we can go beyond the means. Intuitively, one might expect that more moment improve tail control, so therefore improve the optimal stopping guarantee. And the theorem here says no. So in plain language, even if the algorithm is given any number of moments, even the entire infinite moment sequence is given, you cannot guarantee better than and big O 1 over log n in the worst case. Since we show that one moment is already enough to achieve theta 1 over log n, so the best possible guarantee from moment information is theta 1 over log n. I mean, the one moment gives omega 1 over log n. That is wrong. So the curve is actually flat. So the adversarial trick, if we extend this to a higher moment, is basically you want the moment to match. So we wanted the distributions that look identical to the algorithm because their first k moment agree, but their expected maxima over many copies are very different, as shown here. And here's the construction idea. We can start with the discrete long shot distribution of k supported on 0, 1, and square n to the power 4th all the way up to n to the power of 2k minus 1. There are k point. There are k plus 1 points, and with tiny probabilities on the large scale, on the large points. For probability, alpha is in 1 and 2. For parameter alpha is in 1 over 2, we can define a nearby distribution by changing the point n squared to n to the power of alpha with the and substitute the probability with 2 to n to the power of 1 minus 2 alpha. So this nearly preserves the first k moments because the probability have been carefully chosen. But notice that it changes the expected maximum for an independent copies. The maximum is about n to the power of 2 minus alpha. So by moving alpha, we move the profit scale. So this is a near feasible construction. So that's the idea, but we need the exact matching. So we can fix the base support vector x and do the support transfer to vector y. And ask the probability p alpha on the y, whose the first k moment equal to the base moment, as here shown in this linear system. This is also, as you might be familiar with, is called the Vanderbilt matrices. And so this is like we want vy times the probability equals vx times the probability of x. And we can just solve the probability by, we can just get the probability of y by solving the linear system. So the only, notice that the Vanderbilt matrices are invertible, so there is a unique solution. But the only non-trivial case is probabilistic. So the solution to this linear system might not really be a probability distribution because some probability might be negative. And the technical analysis proves that the correction is small enough so that all the probabilities remain valid, and they're close to the intended long shot probabilities. And after this correction, all the f alpha distributions have the same first k moment, but a block of n cube samples from f alpha has a very specific behavior. So with high probability, the largest useful value is near n to the power of alpha, and the contribution above that is negligible. So this gives us a strong building blocks. Each block is indistinguishable by moments, yet its offline value can be placed at the chosen scale by selecting alpha. And this is the bridge from moment matching to the impossibility construction. So now we can combine the blocks into an adversarial family of worlds. There are theta log n sequences, and in world I, the first I blocks are real blocks with increasing parameters, alpha 1, all the way to alpha I, and later blocks are decoys. And all the distributions across all the world have the same first k moment. So the algorithm cannot know whether the current block is the last meaningful block, whether a larger price is still hidden somewhere. Right, so they cannot tell because they have the equal moments, and realistically, only the last block that is not a decoy matters, and they're indistinguishable. So if beta j is the probability, then the algorithm stops in block j, then beta j's sum to at most one. But a good algorithm for a world I would need to put enough stopping probability near the last real block of that world. So if we argue by averaging over the theta log n world, the comparative ratio would give the average comparative ratio. The comparative ratio would average to big O 1 over log n. So some world must be bad for the algorithm. So this proves the upper bound for every stopping rule, not just threshold rules. So the uncertainty here shown here is structural. Many different futures are consistent with the same moment data. And yeah, now we can send it to infinity. So we can first go beyond and then infinity, not the other way around. It remains us to explain why this is not just a finite k phenomenon. So this is a non-trivial step, but like let's go through it here. So for each fixed alpha, the probability this family of alpha k is tight, and so by Prokhorov's theorem here, tightness is to say that it has a weakly convergent subsequence, and with the limit f alpha with a superscript infinity. And uniform integrability lets the moment pass to the limit. Therefore, every limit distribution f alpha infinity has the same moment sequence as the base limit. So, and this is independent of alpha. So the block behavior also survives in the limit. So even with all the moment, the same indistinguishable world trap remains, as shown before. And this is the full moment theorem. Right, so the negative result is about moment information alone. And we showed that with extra structural assumptions that can help us recover some kind of guarantee, such as momental hazard rate distributions. That is something defined here as h is non-decreasing. And with the first moment, we can get 1 over log n, because this improves the scale of the profit value. We can drop it from a factor of n to log n. Or we can control the growth of some higher moment, and here's noted as the bounded coefficient of variation, or just even more straightforward, we can just control bound the support with the big value b, and for this one, we can just get 1 over 2 with some precision error. So with this, the moment information started to approximate the distributional information that the classical profit inequality assumes. So let me end with the takeaway. In optimal stopping, the profit value is extremely sensitive to rare event, and moments alone, even all moments, do not determine those very well for a better profit inequality. And the tight general guarantee is therefore theta 1 over log n, and this guarantee is already achievable with the first moment, just the expectation. So the open directions are like whether it changes in random order, where we know 1 over e is possible with 0 distributional information, and in ID, or does it change in IID setting? So the conceptual message is moments are not automatically informative for stopping, and they become useful when combined with some structural assumptions. Yeah, that's it. And I hope you liked it. I will be happy to take any questions. Um, so so in this work, we just show some kind of results with the general result, what's achievable, what's not achievable. And to answer your question, okay, so For the MHR one, the algorithm is the same. For the bonding coefficient of variation, the algorithm is a bit different, but still a threshold. It's still a threshold algorithm. And for the bonded support one, we can basically create a mirror instance that's that approximate the real instance well enough. Then we can just do the classic real algorithm. Yeah, but that's not the key message of this work. Any more?
Well, no more questions, then let's thank the speaker again. And
Thanks.